The characteristic verdant hue that defines the terrestrial landscape is a direct optical consequence of a single metallic element situated at the precise center of the most important molecule in biological history. When observing the lush canopy of a rainforest or the simple blades of a suburban lawn, the human eye is registering the presence of element 12, magnesium. This silvery-white alkaline earth metal is the essential architect of the biosphere, serving as the functional core of the chlorophyll molecule. Within the intricate architecture of a chloroplast, magnesium acts as a sophisticated molecular trap, a biological antenna tuned to harvest the kinetic energy of photons arriving from the sun. The porphyrin ring of chlorophyll is coordinated around a central magnesium ion, which provides the necessary electronic environment to capture solar radiation and initiate the process of photosynthesis. Without the specific electromagnetic properties of this single atom, the Earth would be a geologically active but biologically inert sphere, devoid of the primary production of oxygen and the chemical energy that fuels every living organism. Magnesium is the unique instrument that allows the planet to swallow sunlight, transforming the chaotic energy of a distant star into the organized chemical bonds of glucose and the atmospheric byproduct of breathable air. The structural importance of magnesium in the chlorophyll molecule is a result of its specific charge to radius ratio and its ability to maintain a stable, non-reactive presence while facilitating rapid electron transfer. While other metals like iron or zinc could theoretically sit within a similar molecular ring, they possess chemical tendencies that would result in unwanted secondary reactions or insufficient stability under the constant bombardment of high-energy light. Magnesium provides a noble stability in the heart of the leaf, acting as the perfect mediator for the exciton energy transfer that occurs when a photon strikes the pigment. This single atom coordination is the foundation of the global food chain. Every calorie consumed by the human species and every breath of oxygen inhaled is a direct dividend of the magnesium ion's ability to manipulate the quantum states of electrons. The green world is not merely a background for human activity, but a functioning magnesium-based power plant that has operated continuously for billions of years, maintaining the atmospheric equilibrium required for complex life. This biological necessity presents a startling physical paradox when contrasted with the behavior of magnesium in its pure metallic form. While it is the silent engine of the cool, damp world of plants, magnesium is also characterized by its extreme reactivity and its ability to produce a blinding white-hot flame that reaches temperatures exceeding 3,000 degrees Celsius. This white flame was the first artificial sun held in the hands of early photographers, providing a concentrated burst of light that allowed the documentation of history in the absence of daylight. The same element that captures light in a blade of grass releases it with violent intensity when ignited, reflecting its cosmic origin as a product of stellar nucleosynthesis. Magnesium serves as a bridge between the celestial and the terrestrial, functioning as both a stabilizer of life and a source of intense, high-energy illumination. This dual nature, the silent green antenna and the iridescent white flame, is what makes element 12 one of the most enigmatic and essential components of the material world. In the contemporary era, the utility of magnesium has expanded from the internal mechanisms of the cell to the structural skeletons of the most advanced machines. It is the lightest of all structural metals, possessing a density that is 33% lower than that of aluminium, yet maintaining a strength-to-weight ratio that is indispensable for the aerospace and automotive industries. We have moved from a species that merely benefits from the magnesium in the plants we eat to a species that builds magnesium wings to traverse the atmosphere. The integration of magnesium into modern alloys allows for the creation of components that are as light as plastic but as durable as steel, serving as the invisible framework for everything from high-performance racing engines to the portable electronics that facilitate the global exchange of information. We are living in a world defined by the lightness of magnesium, relying on its unique atomic properties to push the boundaries of speed and efficiency. The transition from the biological world to the industrial one requires a total re-evaluation of what is considered a metal. We often view metals as cold, heavy, and inert, yet magnesium is a living element that is constantly circulating through the human body, the oceans, and the crust. It is a material that governs the rhythm of the heart and the flexibility of the muscles, serving as a critical electrolyte that prevents the biological system from entering a state of terminal spasm. The green metal of the leaf is the rhythmic metal of the human pulse, demonstrating an interconnectedness that spans the entire spectrum of life on Earth. To understand magnesium is to understand the fundamental mechanism of energy transfer that defines our existence, from the microscopic scale of the chloroplast to the macroscopic scale of the global economy. To ensure the continued production of high-density scientific narratives that uncover the hidden connections between the periodic table and daily life, the engagement of the audience is a critical component. Supporting the channel through subscription and interaction provides the necessary energetic input to bypass the entropic algorithms of digital platforms. By leaving a comment with the specific phrase "light" and activating the notification bell, the viewer assists in maintaining the visibility of these educational explorations. This support is the catalyst that allows for the deep investigation into the materials that define our civilization, from the forbidden gases of the atmosphere to the solar traps of the plant kingdom. Your contribution is the force that allows us to shine a light on the fundamental building blocks of reality. The physical origin of magnesium reveals a narrative of extreme cosmic violence, synthesized in the final, frantic stages of a massive star's life. Unlike lighter elements produced through standard hydrogen fusion, magnesium requires the intense temperatures and pressures of neon burning, a process that occurs only in stars at least 8 times more massive than the Sun. This stellar pedigree is reflected in the element's abundance. It is the 8th most common element in the universe and the 4th most abundant element on Earth, following iron, oxygen, and silicon. Approximately 13% of the Earth's total mass is composed of magnesium, the vast majority of which is sequestered in the silicate minerals of the mantle. The planet is, in essence, a massive magnesium reservoir, a rocky storage facility for the debris of dead suns that waited for billions of years until the emergence of life provided a mechanism for its biological utilization. The chemical behavior of magnesium in the environment is a study in thermodynamic equilibrium. It is found in staggering quantities in the world's oceans, with over 1 billion tons of magnesium ions dissolved in every cubic mile of seawater. This vast aquatic reserve serves as the primary source for the industrial production of the metal, where it is extracted through electrolysis to become the lightweight components of our technology. The journey of a magnesium atom is a continuous cycle of transformation, from the core of a dying star to the silicate rocks of the mantle, through the erosion of mountains and the currents of the ocean, into the cells of a green plant, and finally into the structural alloys of a spacecraft or the biochemistry of a human heart. It is an element that refuses to remain static, serving as a perpetual traveler through the different states of matter. Furthermore, the role of magnesium as a metabolic conductor is essential for the stabilization of adenosine triphosphate, ATP, the primary energy currency of the cell. In every biological reaction that requires energy, the ATP molecule must be bound to a magnesium ion to become biologically active. This MgATP complex is the fundamental unit of cellular work, driving the synthesis of DNA, the contraction of muscle fibers, and the transmission of nerve impulses. Without magnesium, the energy stored in the cells would be inaccessible, resulting in a total cessation of biological activity. We are, at the molecular level, magnesium-powered engines, utilizing the element to unlock the energy that was originally harvested by the magnesium antennas of the plant world. The connection between the sun, the leaf, and the heart is a closed loop of magnesium-mediated energy transfer. The structural utility of magnesium in the modern world is also defined by its damping capacity, the ability of the metal to absorb vibrations and dissipate energy. This makes it the ideal material for the housings of high-end consumer electronics and the interior components of luxury vehicles, where it provides a sense of solidity and silence that other materials cannot replicate. When a person picks up a modern laptop and notices its surprising lightness and rigidity, they are experiencing the macroscopic result of the same atomic properties that allow magnesium to stabilize the porphyrin ring of chlorophyll. The metal provides strength without the penalty of weight, creating a technological environment that is increasingly portable and efficient. We are moving toward a magnesium age of engineering, where the pursuit of lightweight sustainability is driving the development of new alloys that can replace heavier, more carbon-intensive materials. The narrative of magnesium is thus a story of light captured and light released. It is an element that defines the aesthetic of our planet through the green of its foliage and the brilliance of its fire. It is a material that bridges the gap between the organic and the inorganic, the biological and the technological. As we move through the world, we are constantly in the presence of magnesium's work, whether it is the oxygen we breathe, the food we consume, or the devices we use to navigate our lives. The trap for the sun is the silent partner in every aspect of our existence, a foundational element that has transformed the Earth into a vibrant, high-energy sanctuary in the cold vacuum of space. The following blocks will explore the deep-time cosmic synthesis of magnesium and its historical discovery through the bitter waters of an English farm, revealing how a common mineral became the most sought-after asset for the future of aerospace and human health. Magnesium remains the conductor of the Earth's energy symphony, a metal that has mastered the art of turning starlight into the very pulse of life. The cosmic synthesis of magnesium is an event characterized by extreme thermal thresholds that only occur within the final, high-pressure stages of a massive star's life cycle. While lighter elements like helium and carbon are produced through standard fusion in stars similar to the Sun, the production of element 12 requires a stellar environment of at least 8 to 10 solar masses. In these celestial giants, once the hydrogen and helium fuels are exhausted, the core temperature escalates to approximately 1.5 billion Kelvin, initiating the neon-burning phase. During this period, neon-20 undergoes photodisintegration and subsequent alpha capture reactions, a process known as the alpha process. A neon nucleus absorbs a high-energy gamma photon, releasing an alpha particle, which then fuses with another neon-20 nucleus to create magnesium-24. This nuclear sequence represents the neon-burning shell of the star, a high-velocity assembly line of matter that serves as the penultimate herald of a supernova. Because magnesium-24 is a doubly magic alpha element, possessing a highly stable nuclear configuration, it accumulates in vast quantities within the stellar interior, forming a distinct layer in the onion skin structure of the pre-collapse star. When the massive star finally reaches the ion fusion limit and collapses under its own gravity, the subsequent rebound, the supernova explosion, ejects these newly forged magnesium atoms into the interstellar medium at a significant fraction of the speed of light. This is the deep-time origin of the magnesium found within the Earth's crust. Every atom was once part of the incandescent debris of a dying sun, scattered across light years of space before being incorporated into the molecular cloud that eventually collapsed to form our solar system. The isotopic signature of terrestrial magnesium, which consists primarily of magnesium-24 with trace amounts of magnesium-25 and magnesium-26, provides a high-resolution record of this early galactic history. Specifically, the presence of magnesium-26 serves as a __22__ indicator of the short-lived radioactive aluminium-26 that existed at the birth of the solar system, allowing cosmochemists to date the formation of the first solid objects in the protoplanetary disk with a precision of a few 100,000 years. As the Earth coalesced from this cosmic dust approximately 4.5 billion years ago, the distribution of magnesium was governed by the laws of geochemical differentiation. Magnesium is classified as a lithophile, or __23__ element, meaning it has a powerful chemical affinity for oxygen and silicates rather than metallic iron. Consequently, during the _24, when the Earth's molten interior separated into a metallic core and a silicate mantle, the magnesium did not sink with the iron. Instead, it became concentrated in the mantle, where it remains the fourth most abundant element by mass, following iron, oxygen, and silicon. Approximately 13% of the total mass of the planet is composed of magnesium. In the upper mantle, it is the primary constituent of the mineral olivine, a magnesium iron silicate, and in the lower mantle, it exists in the form of bridgmanite, a high-pressure magnesium silicate that is likely the most abundant mineral on Earth. The planet is not merely a _25_ world. It is a magnesium-dominated silicate engine, where the thermal properties and structural stability of magnesium minerals dictate the dynamics of mantle convection and the movement of tectonic plates. The presence of magnesium in the Earth's crust is the result of continuous volcanic and tectonic recycling. As the mantle undergoes partial melting, magnesium-rich magmas are transported toward the surface, cooling to form basaltic and ultramafic rocks. These geological structures provide the foundational architecture of the ocean floors and the roots of the continents. Through the process of chemical weathering, the magnesium trapped in these volcanic rocks is slowly liberated by the action of carbon dioxide-rich rainwater. The magnesium ions, Mg2 plus Mg2 plus, are carried by rivers into the global oceans, where they have an exceptionally long residence time of approximately 13 million years. This means that an atom of magnesium, once washed into the sea, will circulate through the world's currents for millions of years before being sequestered into the seabed. The oceans currently hold an estimated 1.3 times 10 to the 15th power, 1.3 times 10 to the 15th power tons of dissolved magnesium, making it the second most abundant cation in seawater after sodium. This vast aquatic reservoir is the ultimate outcome of 4 billion years of continental erosion and oceanic deposition, a planetary-scale chemical equilibrium that maintains the ionic balance of the world's waters. The geological narrative of magnesium is also inextricably linked to the long-term carbon cycle and the regulation of the Earth's climate. In the oceans, magnesium ions react with dissolved carbonates to form minerals such as dolomite and magnesite. The formation of the Dolomite Mountains in the southern limestone Alps is a macroscopic testament to this process. These massive mountain ranges are composed entirely of magnesium-calcium carbonate, representing billions of tons of atmospheric carbon dioxide that have been permanently sequestered by the __26__. This mineral stability is what makes magnesium a critical player in the planetary __27__. Over geological timescales, the rate at which magnesium is weathered from the mountains and deposited in the sea regulates the concentration of carbon dioxide in the atmosphere, preventing the Earth from experiencing the runaway greenhouse effect seen on Venus or the permanent deep freeze of Mars. The __28__ history of element 12 is a story of planetary management, where a metallic byproduct of neon-burning stars became the primary agent for maintaining a temperate, habitable environment on a rocky planet. The atomic structure of magnesium, characterized by 12 protons and a valence shell of 2 electrons, dictates its behavior as a highly reactive alkaline earth metal. In the oxygen-rich environment of the Earth's surface, magnesium is almost never found in its pure metallic state. It is always bound to other elements in the form of oxides, carbonates, or silicates. This reactivity is a direct consequence of its low ionization energy, which makes it eager to surrender its two outer electrons to reach a stable octet configuration. This energetic potential is what humans eventually learn to harvest, reversing the billions of years of geological stability to produce the white flame, used in industrial and military applications. However, in the natural world, this reactivity is modulated by the formation of a protective oxide layer, a process known as passivation, which allows magnesium minerals to endure for eons in the crust. The tension between its inherent reactivity and its structural stability is the central theme of its terrestrial existence, allowing it to be both a dynamic participant in the biosphere and a permanent foundation of the lithosphere. The distribution of magnesium in the solar system also provides insights into the habitable zone of planetary formation. Observations of other star systems reveal that the magnesium to silicon ratio, Mg/SiMg/Si, in a protoplanetary disk is a critical factor in determining the internal structure and volcanic activity of the resulting planets. On Earth, this ratio favored the formation of a mantle that is both rigid enough to support a crust and fluid enough to allow for plate tectonics. This magnesium-optimized mantle is what enables the recycling of nutrients and the maintenance of a global magnetic field, protecting the atmosphere from solar erosion. In this sense, the cosmic abundance of magnesium is a prerequisite for a geologically active and therefore biologically viable world. We are living on a planet that was forged in a specific chemical window of galactic history, where the debris of neon-burning stars was provided in the precise quantities required to create a world that can breathe. Furthermore, the study of magnesium isotopes in the deep-sea record allows scientists to reconstruct the temperatures of ancient oceans. Because the rate at which magnesium is incorporated into the calcium carbonate shells of marine organisms, like foraminifera, is temperature-dependent, the Mg/Ca, Mg/Ca ratio in fossilized shells serves as a high-resolution paleothermometer. This data allows for the mapping of the Earth's climate history over the last 66 million years, recording the transition from the __32__ conditions of the Eocene to the ice ages of the Pleistocene. Magnesium is thus a recorder of __33__, a chemical witness that has captured the fluctuations of the global environment within its ionic structure. It is a material that connects the microscopic scale of shell formation to the macroscopic scale of global climate shifts, providing the empirical foundation for our understanding of the planet's past and future. The scale of magnesium's presence is further emphasized by its role in the __34__, the radioactive decay of isotopes within the mantle, combined with the residual heat of accretion, drives the convection of magnesium silicate rocks. This slow-motion circulation, occurring at a rate of a few centimeters per year, is what moves the continents and raises the mountains. The thermal conductivity of magnesium-bearing minerals is the primary variable that determines how quickly the Earth loses its internal heat to space. If the mantle were composed of a different material, the Earth might have cooled and become geologically dead billions of years ago. The persistence of the Earth's internal fire is, in part, a triumph of magnesium's specific thermal and physical properties. We are walking on the __35__ surface of a planet that remains molten and dynamic deep below, a reality governed by the 13% of the world that consists of element 12. As we consider the __36__ aspect of magnesium, it becomes evident that its journey is one of increasing complexity. It began as a high-energy nucleus in a pre-supernova star, traveled through the void of space as cosmic dust, and then spent billions of years as the structural backbone of the Earth's mantle. It was eventually liberated by the forces of erosion to become a dissolved ion in the primordial oceans, where it was first captured by the emerging biological systems to create the mechanism of photosynthesis. This transition from cosmic ash to planetary foundation and finally to biological antenna is a testament to the versatility of the element. Magnesium is the 10% occupant of our planet that ensures its stability, its climate, and its ability to harbor life. It is an element that has moved from the most violent events in the universe to the most delicate processes of the living leaf, providing a continuous thread of energetic transformation that spans the entire history of the cosmos.
The following blocks will explore how this geological giant was first discovered through its bitter presence in a 17th century well, and how its lightweight strength became the catalyst for the aerospace revolution, proving that the fourth most common element on Earth is also its most indispensable lightweight asset. The human recognition of magnesium's unique utility did not begin with the isolation of the gleaming metal, but with a chance encounter with its chemical salts in the early 17th century, marking the transition from medieval alchemy to the empirical foundations of modern medicine. In the summer of 1618, during a period of severe drought in the English village of Epsom, a local farmer named Henry Wicker discovered a small pool of water that had collected in a hollow on the common land. Despite the scarcity of water, his cattle refused to drink from the source, an observation that led to the discovery of the water's intense bitterness. Upon further investigation, it was observed that when this __41_41_ evaporated, it left behind a white, crystalline residue with profound physiological properties. This substance, which became known globally as Epsom salt, was magnesium sulfate heptahydrate, MgSO4x7, H2O, MgSO4x7, H2O. The discovery transformed Epsom into the first true health spa of the modern era, as physicians recognized the salt's efficacy as a purgative and a treatment for internal inflammations. This was the first time that a concentrated magnesium compound was utilized as a systematic medical intervention, providing a chemical solution to the stresses of human biology long before the underlying element was identified on the periodic table. The transition from a medicinal curiosity to a purified element required the pioneering electrochemical work of the early 19th century. Although the existence of a distinct metallic base in Magnesia alba was suspected by chemists such as Joseph Black, it was Sir Humphrey Davy who finally isolated the metal in 1808. Utilizing the massive voltaic pile at the Royal Institution in London, Davy performed the electrolysis of a mixture of moist magnesium oxide and mercuric oxide. This process resulted in a magnesium-mercury amalgam, from which the mercury was subsequently distilled away, leaving behind a small quantity of a previously unseen silvery-white metal. Davy initially proposed the name magnium, but the scientific community eventually settled on magnesium to avoid confusion with the newly discovered manganese. The full-scale industrial isolation of the element remained elusive for several more decades, until the French chemist Antoine Bussy utilized a more efficient chemical reduction method in 1831, reacting magnesium chloride with potassium vapor to produce the metal in a cohesive, metallic form. This shift from laboratory curiosity to a bulk material allowed for the first exploration of magnesium's most striking physical property, its intense, high-energy combustion. The mid-19th century witnessed a technological revolution in the visual arts, driven entirely by magnesium's ability to produce an artificial light source of unprecedented intensity. When magnesium is heated in the presence of oxygen, it undergoes a rapid exothermic reaction, emitting a blinding white light with a color temperature that closely approximates natural sunlight. In 1864, the first magnesium wire was manufactured on an industrial scale by the Magnesium Metal Company in Manchester, enabling the birth of flash photography. Before this breakthrough, photography was restricted to the constraints of ambient daylight, making it impossible to document the interiors of caves, the depths of mines, or the structural details of ancient tombs. The use of magnesium, flash powder, a mixture of powdered magnesium and oxidizing agents like potassium chlorate, allowed archaeologists and explorers to freeze moments in total darkness for the first time. The famous photographs of the interior of the Great Pyramid of Giza and the documentation of the Victorian slums of New York City were made possible only by the violent, instantaneous oxidation of element 12. This white fire was the first step toward the democratization of the image, providing the light necessary to reveal the hidden corners of the world.
As the 20th century began, the strategic focus shifted from magnesium's optical properties to its structural potential, catalyzed by the emergence of the global aerospace and automotive industries. The German chemical industry, led by the company Griesheim Elektron, pioneered the development of Elektron, a series of high-strength magnesium alloys containing aluminium, zinc, and manganese. These alloys represented a breakthrough in materials science, offering a density 65% lower than steel and 33% lower than aluminium. The timing of this development was critical, as the advent of the First World War created an insatiable demand for lightweight materials for aircraft frames and engine components. However, the same reactivity that made magnesium useful for photography became a significant engineering challenge. Pure magnesium is susceptible to rapid corrosion and can ignite if subjected to extreme heat in a finely divided form. The drama of early magnesium engineering was a constant battle between the pursuit of lightness and the necessity of structural stability. The Second World War represented the definitive era of magnesium's industrial mobilization, often referred to as the Magnesium War. The production of the metal expanded exponentially, reaching hundreds of thousands of tons per year as both the Allied and Axis powers sought to achieve air superiority. Magnesium was utilized not only in the structural airframes of fighters and bombers, but also in the production of incendiary munitions. The Luftwaffe's use of magnesium alloy incendiary bombs during the Blitz exploited the metal's high combustion temperature to create fires that were nearly impossible to extinguish with conventional methods. Simultaneously, the United States utilized magnesium for the construction of the B-36 Peacemaker, a massive intercontinental bomber that featured so many magnesium components it was nicknamed the __50__. The engineering triumph of this era was the development of specialized coatings and alloying techniques that suppressed the metal's reactivity, allowing for its safe use in the most demanding flight environments. This period proved that magnesium was not merely a flammable powder, but a foundational material for the future of global transport and warfare. The post-war era saw the transition of magnesium from a military asset to a catalyst for high-performance civilian engineering, most notably in the realm of international motor racing. The 1950s represented the pinnacle of magnesium-intensive automotive design, exemplified by the Mercedes-Benz 300 SLR. This vehicle utilized an ultra-lightweight bodywork made of Elektron magnesium alloy, allowing it to achieve speeds that dominated the racing circuit. However, the inherent risks of the material were tragically demonstrated during the 1955 Le Mans disaster, when a 300 SLR was involved in a high-speed collision that resulted in a catastrophic fire. Because the magnesium bodywork was a combustible material, it burned with such intensity that firefighters were unable to suppress the flames with water, which only accelerated the reaction through the release of hydrogen. This event led to a temporary stagnation in the automotive use of magnesium, forcing engineers to develop more sophisticated fire-retardant alloys and to reserve the metal for internal engine components such as gearboxes and crankcases, where the weight savings remained indispensable, but the risk of ignition was minimized. The quest for the lightest structural metal eventually led to the integration of magnesium into the foundation of the space age and the development of the first intercontinental ballistic missiles. The structural requirements of rocketry are characterized by an extreme sensitivity to mass.
Every kilogram saved in the airframe translates directly into increased range or payload capacity. The Titan and Atlas missile programs utilized magnesium-thorium alloys to maintain structural integrity under the intense thermal and mechanical stresses of atmospheric re-entry. These alloys provided a level of creep resistance, the ability of a material to resist deformation under constant stress, that other lightweight metals could not match at high temperatures. In this capacity, magnesium served as the invisible protector of the first objects sent into the vacuum of space, providing the necessary strength to survive the violence of launch while remaining light enough to escape the Earth's gravity. The metal that began as a __53__ in an English field had become the essential medium for the expansion of human influence into the solar system. The historical evolution of magnesium production also highlights a significant shift in the human ability to manipulate the Earth's aquatic resources. While early magnesium was mined from land-based mineral deposits like dolomite and magnesite, the mid-20th century saw the development of the Dow process for the extraction of magnesium from seawater. This method utilizes the vast, nearly inexhaustible supply of magnesium ions dissolved in the oceans, precipitating them as magnesium hydroxide before converting them into magnesium chloride for electrolysis. This transition made magnesium the only structural metal whose primary __54__ is the ocean itself. It represents a total mastery of the planetary chemical cycle, allowing for a sustainable supply of the metal that is independent of the depletion of terrestrial mines. The __55__ became a story of industrial chemistry, where the salt that makes the ocean bitter was transformed into the light and strength of modern civilization. In the late 20th and early 21st centuries, the __56__ of magnesium moved into the microscopic realm with the development of biodegradable medical implants. Because magnesium is an essential nutrient that is naturally processed by the human body, researchers realized that magnesium-based alloys could be used to create temporary orthopedic screws and cardiovascular stents. Unlike permanent steel or titanium implants, which may require a second surgery for removal, a magnesium implant serves its structural purpose and then slowly dissolves over several months, being absorbed into the bone and tissues as a harmless mineral supplement. This represents the ultimate closing of the loop. The same metal that facilitates the capture of light in the plant kingdom and provides the structure for the most advanced aircraft is now being used to repair the human body from the inside out. It is a material that transitions seamlessly from a structural machine to a biological nutrient, embodying a level of compatibility that is unique among the engineering metals. The history of magnesium is thus a narrative of extreme transitions, from the healing crystalline salts of Epsom to the blinding white flashes of early photography, and from the devastating fires of wartime bombers to the lightweight efficiency of modern aerospace. It is a material that has challenged the limits of human engineering, demanding a sophisticated understanding of chemistry to control its violent reactivity, while harnessing its unparalleled lightness. We have moved from a species that was biologically dependent on the magnesium in the soil to a species that has mastered the extraction of the metal from the sea and the stars. The __57__ of element 12 lie in its refusal to be a static, inert material. It is a dynamic agent of change that has illuminated our history, lightened our burdens, and stabilized our pulse. It remains the __58__ at the heart of our technology, a metal that continues to bridge the gap between the terrestrial needs of biology and the celestial ambitions of spaceflight. The following block will explore the hidden mechanisms of magnesium in the modern body and the portable devices of the digital age, revealing that the __quote_59_ and the __quote_60_ are dictated by the same 12th atom of the periodic table. The functional integration of magnesium into the physiological and industrial systems of the 21st century represents a state of total, yet largely invisible, systemic dependence. While the previous historical narratives focused on the violent oxidation of the metal and its structural mobilization in warfare, the contemporary reality of element 12 is defined by its role as a master regulator of electrochemical stability. Within the human biological framework, magnesium is not merely a passive mineral, but a critical cofactor for over 300 distinct enzymatic reactions that govern everything from the synthesis of genomic material to the maintenance of the electrical potential across cell membranes. The most fundamental of these roles is the stabilization of adenosine triphosphate, ATP, the primary energy currency of all known life. At the molecular level, ATP exists as a highly reactive cluster of phosphate groups that would be unstable and prone to spontaneous hydrolysis without the intervention of magnesium. The magnesium ion, Mg2 plus Mg2 plus, binds to the oxygen atoms of the phosphate chain, neutralizing the negative charge and allowing the molecule to be safely transported and utilized by cellular machinery. This __quote_61_ complex is the absolute prerequisite for every muscular contraction, every neurological signal, and every metabolic pathway, making magnesium the silent guarantor of biological kinetic energy. The rhythmic operation of the human heart serves as the most critical demonstration of magnesium's regulatory influence. The mechanics of cardiac muscle function are dictated by a delicate antagonistic relationship between calcium and magnesium ions. In this biological system, calcium acts as the initiator of contraction. When a nerve impulse triggers the release of calcium into the muscle cell, the ions bind to regulatory proteins, causing the fibers to shorten and the heart to beat. However, for the heart to relax and fill with blood for the next cycle, these calcium ions must be actively displaced and pumped back out of the cellular environment. Magnesium serves as a natural calcium channel blocker, competing for the same binding sites and facilitating the reuptake of calcium into the sarcoplasmic reticulum. Without a sufficient concentration of magnesium, the cardiac tissue would remain in a state of terminal contraction, resulting in a persistent spasm that would lead to immediate circulatory failure. This conductive harmony ensures that the heart maintains a stable, rhythmic output, demonstrating how the fundamental chemistry of an alkaline earth metal dictates the very tempo of human life. Beyond the cardiovascular system, magnesium serves as a vital gatekeeper within the central nervous system, specifically through its interaction with the N-methyl D-aspartate, NMDA, receptor. This receptor is a primary mediator of synaptic plasticity and memory formation, but it is also a potential source of neurotoxicity if overstimulated. Under normal resting conditions, a magnesium ion sits inside the pore of the NMDA receptor, acting as a physical plug that prevents the influx of calcium and sodium ions. Only when a sufficiently strong electrical signal arrives does the magnesium ion pop out of the channel, allowing the passage of ions that trigger a neurological response. This voltage-dependent block prevents the brain from being overwhelmed by background noise and protects neurons from excitotoxicity, a condition where excessive calcium entry leads to cellular death. The presence of magnesium in the synaptic cleft is thus the essential condition for cognitive clarity and the prevention of chronic neurological degradation, serving as a molecular stabilizer that allows for the precise filtration of information. The structural utility of magnesium in the modern technological landscape is characterized by its unparalleled strength-to-weight ratio, which has made it the primary material for the chassis of portable electronic devices and high-performance industrial equipment. In the manufacturing of contemporary ultrabooks and high-end smartphones, Magnesium aluminum and magnesium lithium alloys are utilized to create internal frames that are significantly lighter than their aluminum counterparts, while providing superior structural rigidity. This is achieved through a specialized industrial process known as fixomolding, a technique where the magnesium alloy is heated to a semi-solid, slushy state and then injection molded into complex, thin-walled geometries. This process allows for the creation of laptop shells that possess the thinness of a credit card, but can withstand significant mechanical stress without permanent deformation. Furthermore, magnesium possesses excellent electromagnetic interference, EMI, shielding properties, which protect the sensitive internal circuitry of a device from external radio frequency noise, ensuring the stability of the digital signals that facilitate global telecommunications. In the automotive sector, the pursuit of fuel efficiency and the transition toward electric vehicles have led to a massive increase in the use of magnesium die castings. By replacing traditional steel and aluminium components with magnesium, engineers can reduce the total vehicle weight by hundreds of kilograms, which directly translates into lower carbon emissions for internal combustion engines and extended range for battery-powered systems. Magnesium is now standard in the production of steering wheel cores, seat frames, and gearbox housings. The metal's ability to dampen vibrations is also utilized in the manufacturing of engine cradles and dashboard supports, where it reduces the transmission of mechanical noise into the cabin, providing a more stable and silent driving environment. This transition to lightweighting represents a major industrial shift, where the 12th element of the periodic table has become a critical tool for the mitigation of the global environmental crisis, proving that the fourth most common element on Earth is also its most efficient structural asset for sustainable transport. The unique thermal and electrochemical properties of magnesium also allow it to function as a sacrificial guardian in the protection of the world's metal infrastructure. In a process known as cathodic protection, magnesium ingots, referred to as sacrificial anodes, are electrically connected to underground pipelines, the hulls of ships, and the internal tanks of residential water heaters. Because magnesium is more quote, 68 and chemically reactive than steel or iron, it will preferentially corrode in the presence of water and oxygen. The magnesium atom surrenders its electrons to the surrounding environment, creating a small electrical current that prevents the steel from oxidizing. The magnesium quote, 69 itself, dissolving into the water over several years, while the critical infrastructure remains perfectly intact. This invisible mechanism prevents billions of dollars in corrosion damage every year, demonstrating how the inherent reactivity of the metal can be harnessed to ensure the permanence of the built environment. The optical legacy of magnesium continues in the modern world, through the specialized field of pyrotechnics and the manufacturing of high-visibility flares. When magnesium burns, it does not merely produce heat. It undergoes a rapid transition into magnesium oxide, a process that emits a broad spectrum of electromagnetic radiation, including a powerful concentration of visible white light. This is due to the phenomenon of incandescence, where the solid particles of magnesium oxide produced in the flame reach temperatures where they glow with a brilliance that can be seen for miles. In the context of maritime safety and military signaling, magnesium-based flares remain the standard for emergency communication, providing a reliable, high-intensity light source that requires no external power. The same chemistry is responsible for the pure, brilliant white sparks seen in professional firework displays, where the combustion of magnesium provides the necessary quote, 70 that allows the more colorful chemical salts to be seen with greater clarity. Every burst of white light in the night sky is a macroscopic recreation of the same energetic release that occurs when magnesium facilitates the capture of light in the plant kingdom. The role of magnesium in high-end sporting equipment further illustrates its status as the quote, 71 . In the professional cycling and tennis industries, magnesium alloys are utilized to create frames and rackets that offer a unique combination of stiffness and shock absorption. The low density of the metal allows for larger, more aerodynamic cross-sections without the weight penalty of traditional materials, providing athletes with a competitive advantage in environments where every millisecond is critical. This application relies on the metal's crystalline structure, which allows it to dissipate the energy of an impact more effectively than carbon fiber or aluminum, reducing the physical strain on the athlete's joints. Whether it is in the frame of a Tour de France bicycle or the internal components of a Formula One car, magnesium is the silent mediator of human and mechanical performance, pushing the limits of what is physically possible through the management of mass and momentum. The manufacturing of magnesium itself is an energy-intensive process that reflects the global distribution of the element. Approximately 85% of the world's magnesium is currently produced in China using the pigeon process, which involves the thermal reduction of magnesium oxide with silicon at high temperatures in a vacuum. This process utilizes dolomite, a common magnesium-calcium carbonate rock, as its primary feedstock, effectively mining the ancient mountain ranges of the world to produce the lightweight components of modern technology. The transition toward more sustainable production methods, such as the electrolysis of magnesium chloride derived from seawater, represents the future of the industry. This would allow for the production of magnesium with a near-zero carbon footprint, utilizing the vast, renewable reservoirs of the oceans to feed the demands of a global economy. The _quote_72_ of the magnesium supply chain is thus a story of geological extraction and chemical refinement, moving the element from the silent mountains to the center of the technological world. In the realm of advanced energy storage, magnesium is being investigated as a potential successor to lithium in the next generation of battery technology. Magnesium-ion batteries offer several theoretical advantages, including a higher energy density and a significantly lower risk of thermal runaway and fire. Because the magnesium ion carries a 2+2+ charge, compared to the 1+1+ charge of lithium, it can theoretically store twice the amount of electrical energy in the same volume. Furthermore, magnesium is far more abundant and easier to recycle than lithium, offering a more sustainable pathway for the electrification of the global economy. The primary challenge remains the development of electrolytes that can efficiently transport the larger magnesium ions, a puzzle that is currently being addressed by the world's leading materials scientists. If successful, the magnesium-ion battery would transform element 12 from a structural material into the primary fuel for the renewable energy revolution, once again positioning it as a trap for energy on a global scale. Ultimately, the presence of magnesium in our lives is characterized by its role as a universal conductor of stability. It is the atom that allows the heart to relax, the brain to filter information, the laptop to remain light, and the ship's hull to remain uncorroded. It is a material that operates at the intersection of biology, chemistry, and physics, providing the necessary energetic and structural foundation for the complexity of the modern world. We have moved from a species that was merely sustained by the green antenna of the plant world to a species that has mastered the entire life cycle of the element, from the deep-sea extraction to the high-tech alloy. Magnesium remains the silent architect of our daily experience, an element that demands a sophisticated understanding of the material world to truly appreciate its contribution. The final block will explore the existential finality of magnesium's story, following these atoms as they cycle from the mountains to the sea and back into the geological record, revealing the ultimate fate of the element that turns sunlight into life. The ultimate narrative of magnesium is characterized by a state of perpetual geochemical recycling that operates on timescales far exceeding the duration of the biological era. While human civilization has learned to extract and utilize the metal for structural and physiological purposes, the vast majority of the Earth's magnesium remains locked in a slow-motion transit between the deep interior and the planetary surface. This cycle begins in the high-pressure environment of the mantle, where magnesium is the dominant cation in the silicate minerals that dictate the mechanical behavior of the planet. As tectonic forces drive the subduction of oceanic plates into the depths, magnesium is carried back into the mantle, only to be resurrected millions of years later through volcanic outgassing and the formation of new crust. This is the quote 75 for element 12, a material that has served as the structural foundation of the Earth since its accretion 4.5 billion years ago, and will continue to circulate long after the thermal energy of the core has diminished. Magnesium is not a resource that is consumed in the traditional sense. It is a permanent planetary asset that merely changes its mineral form as it moves through the different layers of the Earth. The most visible and massive monument to this geological stability is found in the Dolomite Mountains of the southern limestone Alps. These vast mountain ranges are composed almost entirely of dolomite, a sedimentary carbonate mineral with the chemical formula CAMG, open parenthesis, CO3, close parenthesis, 2, CAMG, open parenthesis, CO3, close parenthesis, 2. The existence of these mountains represents a profound historical mystery, known to geologists as the quote, 76, While the oceans currently contain a staggering surplus of dissolved magnesium, the modern formation of dolomite in marine environments is extremely rare. Yet the geological record contains massive sequences of this mineral spanning thousands of meters in thickness. It is now understood that these mountains were formed through the interaction of magnesium-rich fluids with ancient limestone reefs over millions of years, a process that effectively quote 77 billions of tons of atmospheric carbon dioxide into a solid, magnesium-based crystalline matrix. The Dolomites are thus a physical archive of the planet's ancient carbon cycle, representing a state of absolute structural memory where the 12th element has preserved the chemical history of the atmosphere within the weight of the stone. The role of magnesium as a stabilizer of the global environment is also manifest in the process of silicate weathering, which serves as the Earth's primary long-term thermostat. As rainwater containing dissolved carbon dioxide falls upon magnesium-rich volcanic rocks like basalt, it triggers a chemical reaction that converts the atmospheric gas into bicarbonate ions and dissolved magnesium. These ions are transported by the global river systems into the oceans, where they are eventually sequestered as carbonate sediments on the seafloor. This sequence is the fundamental mechanism that prevents the Earth from experiencing the runaway greenhouse effect that transformed Venus into a pressurized furnace. Magnesium is the chemical hand that reaches into the atmosphere to pull out the excess carbon, ensuring that the planet remains within the narrow temperature range required for the existence of liquid water and complex life. The habitability of the world is, in every sense, a byproduct of magnesium's refusal to remain inert when exposed to the elements of the surface. In the eventual projection of the solar system's history, the fate of magnesium is dictated by the terminal evolution of the Sun. In approximately 5 billion years, as the Sun expands into a red giant and subsequently collapses into a white dwarf, the Earth will be subjected to temperatures and pressures that will dismantle its current geological and biological structures. However, because magnesium is a relatively heavy and stable element, it will be among the primary constituents of the quote 79 that remains. In the white dwarf stage of stellar evolution, magnesium atoms often sink toward the center of the dense stellar remnant, or become concentrated in the thin outer atmosphere of the star, where they can be detected by the high-resolution spectroscopy of distant observers. This signifies that the magnesium forged in the neon-burning phase of a massive star billions of years ago will eventually return to a stellar environment, completing a cosmic journey of incredible complexity and duration. The elements that enabled the capture of light on a rocky planet will once again be a participant in the physics of a dying sun. The existential conclusion of the magnesium story is found in its role as a underscore underscore quote underscore 80 underscore underscore between the organic and the inorganic realms. We are a species that exists within a specific chemical window provided by the abundance of element 12. We walk upon a magnesium mantle, breathe oxygen produced by magnesium-mediated photosynthesis, and rely on magnesium to regulate the very electrical impulses that constitute our thoughts and our heartbeat.
We have learned to harness the metal to build the quote 81 of our aerospace age and the quote 82 of our digital infrastructure, utilizing its unparalleled lightness to overcome the constraints of gravity. Yet, despite this technological mastery, we remain temporary participants in a much larger magnesium cycle. The atoms of magnesium currently circulating in our bloodstream and stabilizing our DNA were once part of the ancient oceans and the silicate rocks of the mantle, and they will eventually return to those reservoirs after our biological processes have ceased. The underscore underscore quote underscore 83 underscore underscore of magnesium is also evident in its use as a primary material for the documentation of human history. From the magnesium-based flash powders that allowed the first photographs of the dark places of the world, to the magnesium alloy frames that protect the servers of the global internet, the element has always been a facilitator of human record-keeping. It is a material that provides the light to see and the strength to preserve. Even in the realm of fine art, magnesium compounds are used to stabilize pigments and to create the structural supports for sculptures that are intended to last for centuries. This is the underscore underscore quote underscore 84 underscore underscore of magnesium, a refusal to participate in the rapid decay of organic matter, providing instead a cold, metallic foundation for the endurance of information and culture. Looking trillions of years into the future, long after the stars have ceased to form and the universe trends toward a state of maximum entropy, the individual atoms of magnesium will remain as stable, coherent units of matter. Unless the proton itself is subject to decay, the magnesium nucleus, composed of 12 protons and its complement of neutrons, will persist in the darkness of a frozen universe. These atoms will be among the last underscore underscore quote underscore 85 underscore underscore structures in existence, representing the final remnants of the energetic era of the cosmos. The quote 86 that once illuminated the human story and the quote 87 that once fueled the Earth's biosphere will be reduced to individual, indestructible bullets of matter, drifting through an infinite void. This is the ultimate fate of the element, to be the second to last witness to the history of the universe, a material that survived the fire of the stars and the complexity of life, to become a permanent monument to the existence of matter itself. The paradox of magnesium is that it is both a catalyst for violent energy release and a guarantor of biological and geological peace. It is the element of the quote 88 and the quote 89, the quote 90 and the quote 91. It has allowed the Earth to become a vibrant, high-energy laboratory for the development of complexity, providing the necessary energetic bridge between the sun and the cell. We have moved from a state of total ignorance regarding this underscore underscore quote underscore 92 underscore underscore to a state of total dependence on its structural and electrochemical properties. Our civilization is, in a very literal sense, a magnesium-reinforced structure, built upon the fourth most common element in the world. As the narrative of element 12 concludes, the focus returns to the objective reality that we are merely a momentary chemical error that has learned to utilize this ancient underscore underscore quote underscore 93 underscore underscore for a brief period of time. The final conclusion of the magnesium narrative is one of profound environmental and physical integration. Every breath of oxygen, every calorie of food, every rhythmic pulse of the heart, and every lightweight device in the palm of a hand is a manifestation of magnesium's unique atomic architecture. It is the conductor of light that turned a cold, rocky planet into a blooming sanctuary,
and it remains the primary engine of planetary habitability. The 13% of the world that consists of magnesium is the silent partner in our survival, a material that has mastered the transformation of starlight into life. As we look out upon the green world and up at the white stars, we are seeing the two ends of the magnesium journey, a cycle of energy and matter that defines the very boundaries of our existence. Magnesium is the eternal mediator, the non-reactive anchor, and the brilliant flame of the periodic table, an element that has shaped the history of the universe and continues to dictate the rhythm of our hearts. This is the ultimate legacy of element 12, to be the foundational material that allowed the universe to see itself through the mechanism of life. By trapping the sun's energy in a green leaf, magnesium provided the caloric foundation for the development of consciousness, allowing a biological species to eventually look back at the stars and understand the neon-burning origin of the very atoms in their own bodies. We are the consciousness of magnesium, the temporary biological expression of a metal that has been working for billions of years to stabilize the world. When the final atom of magnesium on Earth eventually returns to the geological record, it will carry with it the memory of its transit through the biosphere, a silent witness to a planet that once glowed with the light of a captured sun. The white flame will finally go out, but the stone of the Dolomites and the silicates of the mantle will remain, cold and indifferent, as the permanent graveyard of a once living world. This is the existential finality of magnesium, the element that gave us everything, and will be the only thing left when everything else is gone.